Hello and welcome to Toddcast number 35. My name is Todd Bennett, and to date, as far as nucleophilic substitution goes, we did general definitions in Toddcast 33. We looked at the SN2 reaction in Toddcast 34, and so we'll look at the SN1 in Toddcast 35. And whereas the SN1, as far as the reaction goes, can actually be considered a little more simple than the SN2. It has rearrangement, which can get it complicate things pretty quickly. So we're going to look at the mechanism, which will overall be a two-step process instead of the one step that we saw with SN2. And we'll have to, at that end of the first step, consider the stability of the intermediate before moving on with the second step. And that hopefully it all makes sense very, very soon. Okay, so for the SN1 mechanism, we call it the SN1 because it only depends on one thing as opposed to two. So the reaction always depends on electrophile. Electrophile always has to be involved because that's what's giving up a leaving group. And the SN2, the nucleophile affects the rate, and the SN1, the nucleophile has absolutely no bearing on the rate of the reaction. It just sits around and waits to attack the carbon with the positive charge carbocation once the leaving group has completely detached from the carbon. Okay, those are our views of an SN1, SN2. There are those who argue that reality is it's a continuum, not an absolute SN1 or SN2, but there's some range, and that probably makes a little more sense. But at our level, or this level of organic chemistry, we're going to say it is an extreme. It's either the SN2 or the SN1. Okay, so still want to consider the exact same things we do with any nucleophilic substitution reaction, and that is first consider the electrophile. In this case, electrophile is a carbon with a bromine, so it's got a good leaving group, and it has 1, 2, 3 other carbons attached, so it is a tertiary carbocation. Tertiary carbocations are too crowded to go by SN2, so they go by SN1, where just for whatever reason, this leaving group leaves. It starts here and turns into a lone pair on bromine, so lone pairs are now 1, 2, 3, and 1, 2, 3, 4, so it increased by 1. Takes electrons with it, so it gets a negative charge. If the bromide is negative, it leaves behind a carbocation. Now you'll notice that it went from sp3 hybridization to trigonal planar, so it's sp2 with an empty p orbital. The rehybridization actually helps with the stability. So if we draw the energy diagram, which we will, it's going to take energy to break the bond, but we're going to get a little bit of energy back in the less steric hindrance and the rehybridization of that central carbon. Okay, second part of the reaction, second step, we now have to consider how stable this is. A tertiary carbocation is more stable than secondary. Secondary is more stable than primary. There's no resonance to consider. So we're going to look at all the other carbons. These carbons are primary and primary. This carbon is secondary. So tertiary is the best it's going to be. So there's no need for it to rearrange. It already is in the best possible state. Okay, so now that it's not going to rearrange, we have the tertiary carbocation. The nucleophile, as mentioned here, is free to attack from either side, meaning this is a planar carbocation. So if I draw the plane of it perpendicular to the plane of your page, the nucleophile can come in from the left side or come in from the right side. So if it comes in from the left, goes from that position, so it ends up coming left and pushing these over. So it looks almost like the SN2 inverted product. But it also is free to come in from the right side, where if it comes in from that side, it just pushes them right back to where they were. So they're back in the original position over here. Okay, so 2 steps. It leaves. We check to see if there's any potential rearrangement. And if there isn't, then it attacks the most stable carbocation it can possibly form, forming new bonds either on the right side or the left side. Normally, we'd have to consider its RRS, but these two groups are identical. These two groups are identical, so there is no RRS to consider. But if there were chiral centers, well, because this is planar, we'd expect it to attack half time on the left, half time on the right, meaning half time it would be R, half time S. You'd end up with a racemic mixture. So racemic mixture is a telltale feature of an SN1 reaction. So again, it occurs in two steps with a carbocation that has an actual measurable lifetime, so you can detect it in the middle. And then generally speaking, the more stable carbocations are the ones with more groups donating to them. So tertiary, more stable than secondary, secondary, more stable than primary. Primary and methyl just don't exist. You can force a primary carbocation under extreme conditions. Methyl carbocations you just can't force. So carbocations are either going to be, for our intent purpose in this class, secondary or tertiary. Okay, so visualizing it. Again, I like the fact that it can do animation. So here's our initial molecule. Rather than having something coming in and pushing it off, it's just going to leave. When it leaves, the repulsion of the bromine to these three bonding pair of electrons goes away. So they're free to spread out. Instead of being close to each other, 109.5, they can spread out. So that bromine is going to pull away from the electrophile. So leaving is going to leave. So again, want to show the energy diagram. The difference is there are now two steps. Steps intermediate before going to product. The one has nothing to do with number of steps. The one has to do with the number of reactants that affect the rate. So in this case, only one. Reaction order is first order, so it only depends on the electrophile. The nucleophile just sits around and has no impact on anything. Okay, so that's our starting point. That's our reactant. It is going to reform a little bit as this bond starts to break and this leaves. These carbons are going to move over, and it's going to be a little less crowded here. And you're going to get a delta plus and a delta minus because you're breaking in a heterolytic fashion where both electrons are going to one side. So you go through a transition state, but then once the bromine is completely detached, then it can get a little more stable because of that repositioning. So now we have my carbon here is sp2, and it's a trigonal planar, so there's less steric hindrance, so it actually goes down. I've exaggerated a little bit. If you draw the energy diagram, it really doesn't go down as much as that, but just want to emphasize that we're now at the intermediate stage. Okay, so now lead group is gone, the nucleophile can come in. So this sulfide, good nucleophile, don't have to have a good nucleophile or bad nucleophile. Any nucleophile will do because this is going to be so reactive. Again, it can attack from left or attack from right. I'm only going to show the left side because that's where it's drawn on there, but it's the same thing. It can happen simultaneously on a different molecule, on a different carbocation. So this nucleophile is going to start to form a bond. You're seeing some interaction. So as it gets closer, you'll see it get a little bit closer and start to form a bond. And that's where you have your next transition state. And then finally, as this forms a full bond, that negative is going to go away. It's still going to be partially because it's a little more electronegative than carbon, but not as extreme. So it's going to come in a little bit further. When it does, it's going to actually form the bond, and here is your product. And again, it could attack from either side. Okay, that's your visual. So what matters? Again, same systematic approach. What matters before? Tertiary, so it's a crowded electrophile. So it definitely wants to go by SN1 and solvent. In this case, because you do have a carbocation, you want it to be stabilized, and hydrogen bonding is a stabilizing factor. So typically, protic solvents help. So solvents like ethanol would help this go. Just in general, alcohol solvents would be a good for this reaction. During, you have three things attached, which means you always have to consider the potential for rearrangement. So in this one, I've changed the structure slightly. Notice it is no longer CH2, CH3, CH3. It's now three different R groups. So we have an isopropyl, an ethyl, and a methyl. We do have the potential for rearrangement. So if it rearranged here, it'd be secondary, rearranged here, primary, rearranged to any of these primary, rearranged to this one though. If that H moved over, it could go tertiary to tertiary. So I'm going to ignore it for this example, but when you have two possible things of equal substitution, you're going to get a mixture of both. But if it is just this, then again, the nucleophile is going to attack either from left or right. And now because I have three different substituents, it is going to make a difference. So let's say I'm going to use a different nucleophile this time, OCF3, so that we can distinguish it from the rest. Attached from the left, it goes this side and pushes those over. Attached from the right, pushes here and pushes those to the left. So notice these are opposite of one another. Priority number 4 is in back, so that works out well. So priority 1, 2, 3. So R. Priority 1, 2, 3. So S. So racemic mixture, you get 50% R and 50% S. So just want to emphasize racemic mixture, 50% of each, the R and the S. Okay. And then rearrangement, yeah, I should have considered it here. This shows no rearrangement in this product, but reality is I would have probably also gotten a little bit of H3C, H3C, and nucleophile we just added, OCF3. We'll put it out like this, and then the rest of the structure from here, which would have been, this lost its H, so the H is gone, it's moved over here. So I have a CH, and on that CH, I would have a CH2, CH3, CH3, that's this group here, this group here. This one I don't worry about racemic because these two groups are identical. There's no chiral center. So rearrangement would have gotten me a small amount of this. So it might have been, let's say, 48%, 48%, and 4%, or something like that, some distribution. Fast or slow, because you wait around for the group to leave, it is always a slow reaction. SN2s are always fast. SN1s like this are always slow. So the rate only depends on electrophile. So there's about a factor of 100 difference. Well, I want to be careful saying that because it also depends on the solvent and a few other factors. But with comparable solvent and comparable temperature, you could expect about 100, factor of 100 difference. So what happens with rearrangement? Do you actually want to look at that a little more carefully? So in this case, we have an alcohol. OH is a terrible leaving group. So if I just said it did this, I'm wrong. You lose points. You have to make it a better leaving group. So OHs, you go to a lot of trouble to make them better leaving groups. The one thing we've covered so far is you can protonate it. So if I add acid, a mild acid, then I can turn it into water. Okay, it is on a secondary carbocation. So, or a secondary carbon that can become a carbocation. Again, that's could go either way. So I'd have to make the conditions favor SN1. Protonate it, make it a much better leaving group. Protic conditions, acidic conditions, that will definitely have a tendency to favor SN1, the solvent. So we're going to protonate it first and foremost. So I have to have some form of acid, mild HCl, something, but, or not mild, but low, like medium or reasonable concentration HCl. Going to protonate it. Water is a really good leaving group. So water is going to leave. And we have this secondary carbocation. Okay, so can it become a more stable carbocation? So if I look to the H's to the left and to the right, if the H here moves over, this will now have an H, this will positive, that would be secondary, nothing gained. But if this H moves over, if this H travels to this spot, then we will have this carbocation. So that H moved over, so H is now here, and I don't know which H it is because it's identical to the one that is already there. So it could be a front, one being back, but I'm emphasizing the one single H moved over. Note that there are two H's on the structure. So if I wanted to be a little more precise, then I should put H like this, and H like that, but noting that the one that migrated is one of those. Now it's a tertiary carbocation, which means it's an improvement, it's more stable. Rearrangement is always faster than nucleophile coming in because it's easier to change your seat than for somebody to come all the way across the room and sit in that seat. So it's going to move over, become tertiary, and then the nucleophile. So nucleophile, let's say it's SH with CH3, and S lone pair is going to come in and attack. When it does, you now have 3 bonds of sulfur, so positive charge. It's going to deprotonate and give back the H+. So the H+ you used in the beginning was catalytic. So I should note that plus H+ in the end. So the same H+ I invested there, same one I'm regenerating in the end. So it's a catalytic H plus, not a reactive or stoichiometric H plus. Okay, so same set of rules. Secondary could go either way. So I look at the rest, not necessarily a good nucleophile, but proto conditions. So proto conditions is going to favor the SN1. I have to look at the carbocation. Going from secondary to tertiary is an improvement. So it will rearrange to get a better situation. We're definitely going to have that pop up as one of the things in this class repeatedly. Is there a racemic mixture? Real question, is there a new chiral center? Well, CH3 and CH3 are equal, no new chiral center. So therefore, can't be racemic. That covers this, and hopefully you're starting to see the nuances between one and the other. The tricky part is when you're given one and you blindly have to decide if it's SN1 or SN2, and that's where we're going to be going in future Toddcasts. But for now, just going to call it a Toddcast. So thanks for joining in, and I will see you at 36. Bye.